Good morning, students. This is Shivan Birada. I am a PMRF PhD fellow in Control and Automation Department at IIT Delhi. So the first week of the NPTEL lecture covers the topics like vector spaces, subspaces, and basis and dimension. So I'll be taking 15 to 20 minutes to cover up the basics with some examples, and then I'll take around 10 questions, model questions, which will solve and that will help you to understand the concept. So we'll see what is linear combination first, and we'll slowly develop on this concept, and then we'll cover vector spaces, then subspaces, then basis, and then dimension. So let us say that there are n vectors in RM dimension. So let us take an example here. I'll go with the examples. Okay. So this means that you have, okay, let's start with this. So this means that you have a line, a simple line. So this R1 represents this space, this line. What if you do this 1 plus 1? This would be like adding one more line perpendicular or orthogonal to this line. So this will be R2 space. So we call this as an R2 space. So let us consider we have n vectors in Rm space. So we say that the vectors v1 to vn are linear combination of v1 to vn if there exists a scalar x1 to xn such that v equal to summation xi vi for all I is equal to 1 to n. So basically what we are doing is that, let us say that we have a space R2. So this is my space R2. And we have two vectors. Let us say this vector is 1, 0, and this vector is 0, 1. So the linear combination of vector v2 and the linear combination of vector v1. So the linear combination of these two vectors, alpha 1 v1 plus alpha 2 v2, where alpha 1 and alpha 2 belongs to a real number. So this real means alpha 1 and alpha 2 are coming from this line. So the linear combination basically means that this, like, I'm multiplying a scalar element with a vector and then adding them. So this is called the linear combination. So we can take this vector. Let us say that v is 3 to 4. We can express this vector v 3 to 4 in R3. So we are considering R3 here, which means that this is a three-dimensional plane now. So we are considering R3, and in R3 we have a vector 3 to 4. So this 3 to 4 can be expressed as a linear combination of v1, v2, v3, which means that v can be written as alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. So you have to find what is alpha 1, alpha 2, alpha 3 such that the linear combination of these three, v1, v2, v3, will give us this vector v. So what is linear independence? So this linear independence is directly related to your definition of this definition, linear combination. So let us say that we have two vectors v1 and v2. So you have to check that alpha 1 v1 plus alpha 2 v2 is equal to 0. So here what you have to do here is that for what value of alpha 1 and alpha 2 this becomes 0. If this is true for some value of alpha and alpha 2, then we see that v1 and v2 are linearly dependent. If this is not true for any value of alpha 1 alpha 2, except alpha 1 equal to 0, alpha 2 equal to 0, then we say that v1 and v2 are linearly independent. So what does this mean in R2 space? So let us consider this example. So let us say that we have this vector, say 1 comma 0, and this vector, say 0 comma 1. So are these vector linearly independent or linearly dependent? So 0 1 and 1 0, right? So alpha 1 0 1 plus alpha 2 1 0. So you can see that there are no value of alpha 1 and alpha 2 for which this will become 0, except alpha 1 equal to 0, alpha 2 equal to 0, which is not allowed here. So this vector and this vector are linearly independent. So let us take another example in the same space. Let us say that we have this vector and we have this vector. So this is 5 comma 0. Let us say this. So are this vector and this vector linearly independent or linearly dependent? So say alpha 1 is 1 comma 0 plus alpha 2 is 5. So if alpha 1 equal to 1, no, sorry, alpha 1 equal to 5 and alpha 2 is equal to 1, alpha 1 equal to minus 5 and alpha 2 equal to 1, alpha 2 is equal to minus 1 and alpha 1 is equal to 5, then this linear combination would be 0. So there is some value of alpha and alpha 2 for which this linear combination is 0, which means that this vector and this vector is linearly dependent. So in figure, the linearly dependent vector looks like they're parallel to each other. They coincide with each other. So we'll see. So again, this span is dependent upon the linear combination. It's very closely related to the definition of linear combination. So let us say that we have n vectors v1 to vn in some space. So the span of these vectors v1 to vn is defined as the set of all the linear combination of these vectors vn to vn. So what does this mean? So I'll take an example again. So let us say that I have a vector 1 0 and I have a vector 0 1. So what is the span of these two vectors? The span of this vector is set of all the linear combination of these two vectors. So 0 1 plus alpha 2 1 0. So take any value of alpha 1 and alpha 2, put it here, you will get a vector. So that will be your span. So this set has infinite number of elements. This set has infinite number of elements because you can take any value of alpha 1 and alpha 2 and you can generate a vectors in this space. So like if alpha 1 equal to 1 and alpha 2 equal to 1, then you will get this vector. If alpha 1 equal to 2, alpha 2 equal to 2, then you will get this vector. So this is what your span. Basically, span is set of all the linear combination of the vectors. So what is the basis of Rm? So again, we are in m-dimensional space. So we'll, for our convenience, we'll see at R2-dimensional space only. So I'll directly jump onto example and let us see that. Let us consider that I have one vector here and this is 1 comma 0. So if I multiply this vector with 5, then I'll get a vector 5 comma 0. If I multiply this vector with minus 5, I'll get a vector at minus 5 comma 0. If I multiply this vector with minus 10, I'll get another vector minus 10 comma 0. So just by using this vector 1 comma 0, I can generate this whole line itself, this whole line. So now I say that this vector 1 0 spans R. So now let us take another vector here. I'll say this is 1 0. 0, 1. If I take a linear combination of these two, let us say that linear combination would mean that alpha 1, 0, 1 plus alpha 2, 1, 0. Then this would be alpha 1, alpha 2, alpha 1. So if alpha 1 equal to 2 and alpha 2 is 3, then I'll get a vector something like this. You can take any value of alpha 1, alpha 2 and you can generate any vector here. So what what is happening here is that just using these two vectors 1, 0 and 0, 1, you can span the whole space. Right? So let us consider a final example to understand the concept of basis. So let us take that I have 1, 0 and I have another vector 2, 0. So if I add these two vectors, I'll get another vector on the same line 3, 0. If I subtract these two vectors 1 minus 2, that will be minus 1 comma 0. So if I do these operations here, or if I let us say that I multiply this vector, then I'll get this vector by minus 5, then I'll get minus 5 comma 0. So to generate this space or this line, I need just one vector. So that vector can be 2, 0, or that can be 1, 0, or that can be minus 1 comma 0, or that can be minus 5 comma 0, or that can be 3 comma 0. So there is only one vector needed to span this whole line. So that is your basis. So we can take 1, 0 as your basis, minus 1 comma 0 as your basis, or minus 5 comma 0 as your basis. So to span this line itself, we need only one vector, and that vector is your basis. So what is the basis for this vector? So what is the minimum number of vectors which can span the whole space? So this will be 1 comma 0 and 0 comma 1. So these two vectors can generate the whole space. Only these two vectors. If you take this vector, let us say if you take this vector 1, 1. So are these three the basis, or only these two are basis? So what? So you can see that addition of this and this would give us this. So basically, this is linearly dependent on these two vectors. So I'll cancel this vector. So now I'll have this vector and this vector. So there are only two vectors which are needed to span this whole space. So we say that this and this are basis of this. And remember, bases are not unique. For example, 1 comma 1 and a line perpendicular to this vector. These two are also the basis. This vector and this vector is also the basis. So bases are not unique. So now you understand that what is basis. So basis is minimal number of vectors which can span your whole space. And the minimal number of vectors is your dimension. So as I said, for spanning this line, you need minimum one vector. So that one vector, the number of such vectors are called the dimension. So dimension to span this space is 1, and dimension to span this space is 2, and extending this, the dimension to span this space would be 3. So this was the basic, and now we'll go on to some problems. So let us consider a vector space V in R3. So this would be your three-dimensional space. So in three-dimensional space, you will have all the vectors, 3D vectors. So the question here is that which of the following set is not a spanning set? Is not a spanning set. So what does this spanning set means? So the spanning set basically means that you have some vectors in this R3 and you take a linear combination of those vectors. and it has to span that space. So remember that R3 has three things, here. This one and this one. This is X, Y, Z. So in R3, in this whole space, you can get three things: a line, then a plane, and then any 3D objects. Right. So, okay. So we have which of the following set is not a spanning set. So remember this 100. 100 would mean that X is 1 here, this one, and Y is 1 here, and Z is 1 here. So that point would be somewhere like point would be somewhere here. That would be 1, 1, 1. Right. So this one point these three vectors can span your whole space here, whole R3 dimensional space. You have another vector here. You can do the same thing here. Like you take these vectors alpha 1, 1, 1, 1 plus alpha 2, 1, 1, 0 plus alpha 3, 1, 0, 0. So you'll get a spanning set here. Then you can check the same thing. Yeah. So we'll go on for second question. So what the second question says that let star be a binary operation on the set of real number R and is defined as this. So the question is this binary operation commutative, associative or commutative or both A and B? So what does associative means? Let us say that we have three elements A, B and C. So this is a binary. Remember that this is a binary operation. So this can operate on only two real numbers. So let us say that this is operating on A and B. Close this and then. So associative would mean that A star, B star, C. So are these equal? Do this and find out whether this is associative. I think this is associative. And what is commutative? A star B. Is this equal to B star A? If these are equal, then we say that it's commutative. So the same thing is for this question. You can do it on your own. You can do the same thing in the fourth question. So we have a question number 5. The question says that we want to express this vector in three-dimensional space as a linear combination of vectors v1, v2, v3, such that v is x v1 plus y v2 plus z v3. X, y, and z are your scalars. Then what is the value of x? The simple, I'll give the skeleton of the solution here. So what we have here is that x is a scalar. You have v1, 1, 2, 3 plus y. You have v2, that will be 2, 3, 7 plus z, 3, 5, 6. And this is equal to 3, 7, 9, 4. So the question says that what is the value of x, y, z? In particular, what is the value of x such that you will get this value? So the simple method would be to arrange these vectors 1, 2, 3. This vector here in this, and we'll basically construct a matrix, and then we'll arrange this vector in this first column, this vector in the second column, this vector in third column, and we will put x, y, z. 3, 7, minus. Remember that this is a very important result in the sense that how can we arrange this into this form? So remember this. So now, simple. Find the solution. Find, so this comes like ax equal to b. So you have to find a w is equal to b. You have to find w you'll get X. So we'll move on to sixth question. Let V M N N the vector space of n cross n matrices. Let W1 be the subset of all upper triangle matrices. So which means that let us say that you have this matrix. So these are your diagonals. Let us say that we have 4 cross 4 matrix. So all the upper triangular matrix would mean that this triangle is so the elements in this upper part would not be equal to 0, and all of the elements below this would be 0. So W1 would basically be the space or the subset of all the upper triangular matrices. So this space or subset will contain only upper triangular matrices. And they have said to consider another subset or space where you have only symmetric matrices. So W would have only symmetric matrices. Symmetric. And this would have upper triangular matrices. Upper triangular. So which of the following is true? W1 is a subspace of V. So W1 is a subspace of V. So what is subspace actually? So subspace is that subspace means that let us consider a vector space. So you have a vector space. So this is a space, right? And let us call this a vector space V. You have a small subset of this vector space. Let's say that, and let us say it follows some property. That is closure under addition, and closure under addition, closure under multiplication, and this subspace has 0 element. So if these three properties are satisfied for a subset in a vector space V, then we say that this subset is subspace. So is this being satisfied in? So W1 is a subspace. Yes, that is a subspace. So let us take an example. A1, A2, A3, 0. This is a two-dimensional. Right? I'll take another example. B1, B2, B2. So if I add these two, I'll get another matrix A1 plus B1, A2 plus B2, 0, A3 plus B3. So this is again a upper triangular matrix. So this I get another matrix which is again in this subset W1. So if you add any two vectors here, if you add any two upper triangular matrices here, then you will get another upper triangular matrix in the same set W1. Okay. So we have to check another property. So what is, let us say that I multiply this with a vector gamma. So I'll get gamma A1, gamma A2, 0, gamma A3. Again, I am getting a matrix which is upper triangular matrix in the same subset W1. And another final and important property would check whether zero in this subset or not. Let us say that I have 0, 0, 0, 0. So 0, 0, 0 is obviously a upper triangular matrix, a type of upper triangular matrix. So this has a 0 matrix in this. So W1 is a subspace of. And if you check all the three properties, that is closure under addition, closure under multiplication, and 0 element must be in this subset, then this will be called subspace. And W2 is a subspace of vector space. So this will be the answer. I think this should be easy problem. You can solve this. So now this is an important problem. Let us consider a vector space MN, and this vector space is a set of all n cross n matrices. So I have a vector space V, which has all square matrices, n cross n matrices. And in this space, there are two subspaces. So we have two subspaces in this space. W1 has a property that the elements in the elements in the W1, let us say that we have matrix A here in W1. This matrix A satisfies this property. And let us say that I have an element B in W2. This matrix satisfies this property. So basically, what are they telling is that all the row sum, which means that you have elements like this. I'll add all these elements in columns, in row. So I'll call this row sum. What is this property saying? If I have the elements like this, I'll add all these elements. Okay. So the row sum here is 0 and the column sum here is 0. So the elements in W1 satisfy elements in W1 satisfy row sum. So row sum is equal to 0 and we have column sum is equal to 0. So is W1 union W2 the subspace of B? This is the question. So let us take the union of these two vectors W2. If I take the union of these two vectors, then I'll get another subset. So this would be W1 union W2, which is in this vector space V. So is this now? The question is this a bigger set, a subset of this vector space V, a subspace? So I'll take a simple example here. So let us say that A is this vector and B is this vector. So A satisfies the row sum property, and B satisfies the column sum property. So if I add these two, I'll get this matrix. So the row sum is not equal to 0. 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 Which means that if you add any element in this in subset W1 union W2, so there is no guarantee that the element you get after adding these two elements will remain in this set. So you can get so you will adding two elements can result a matrix which can be outside this subset. This this violates the property of subspace. So now the important question: which of the following sets form a basis of R3? Remember, we are working in three-dimensional space. So in three-dimensional space, so as I told you, for a line, the basis, so you will have one basis to explain this whole or to span this whole set. Sorry, this line. For two-dimensional space R2, you need two vectors to span this, two linearly independent vectors to span this whole space. So the basis for R3 would obviously have three vectors, three linearly independent vectors. So you have only two vectors here. So these two vectors alone cannot be the basis of this. You need another vector to form the basis of this R3. Similarly, check this actually if they are basis or not. Find the dimension of the subspace W of vector space R3. So carefully look at this. A plus B plus C is equal to C. So this is an equation of plane. Equation of plane in R3, three-dimensional space. And remember, there are three vectors. This is X, Y, Z. For generating a plane in 3 dimension, you need only 2 vectors. So if you have these 2 bases, then you can generate a whole plane. So if you have two, let us say that this is 0, 1, 0, this is 1, 0, 0. Take a span of this, you'll get this whole XY plane itself. You'll get this whole XY plane. So to generate a plane, any plane in 3 dimensional space, you need only 2 vectors. So the dimension of the subspace, so the dimension of this space or this subspace of plane would be 2. So this completes the week 1 slides and explanation problems. Thank you very much.